Ladies and gentlemen, thank you for joining us this morning for the Engineering Science session. My name is Erik Birgersson. I'm the Director of the Engineering Science program. With me today, I have Jerome van Kaan, who is the Deputy Director of the Engineering Science program. I have two admin, Joshua and Li Ling. With us here today, two students, Tawakul and Jaren, who'll be able to answer questions on student life and all of that. And our distinguished guests, Ibnur, our former ESP students, now alumni. He's going to talk about a little bit what it's like to be an alumni of the Engineering Science program. Without further ado, let us get started. We have prepared a video that will give you an overview of the Engineering Science program, after which we'll go into shorter presentations, and then we'll open the floor for questions, thoughts, ideas, and we can share information and all of that goes with it. Let me share our video that we have prepared. And let's try that again.
In today's tech-driven society, demand is growing for engineers capable of game-changing research, turning scientific discoveries into marketable products, and working across disciplines. This is where engineering science comes in. Here at NUS, we provide you with the skills and the confidence to thrive in this fast-paced world.
Studying engineering science will give you hands-on exposure to cutting-edge engineering applications combined with strong science fundamentals. Since our cohort size is small, you experience a more personal style of education, forming strong bonds with your peers and professors as you go forward into your career.
I was attracted to engineering science because of its multidisciplinary character, and I graduated from the program in 2018. The design projects particularly helped me to develop hands-on skills, and I liked the fact that many of them were open-ended. This gave students the opportunity to explore different solutions. I went on to do a master's degree project that was run by Tan Tock Seng Hospital and a professor from ESP. This led to my current job in optical imaging for medical devices with A-Star.
This is a coffee cup microphone connected to an audio mixer, connected to an electric guitar, which was made by students in the first year electronics project. In your first 2 years of studies, you'll be exposed to a wide array of fundamental topics in engineering and science. From there, you'll be able to choose your specialization based on your interests and passion, where classroom theory is combined with experiments in design projects and an industrial vacation internship. NUS is a member of an international engineering science consortium with exciting exchange opportunities. Through collaboration with partner universities, you'll have the opportunity to go on exchange and summer internships at institutions such as the University of Toronto and Osaka University.
By studying engineering science, you'll open up a wide range of career options. You can go for further postgraduate studies in top universities around the globe, work in both local and international companies in fields such as health, security, energy and transportation. Or maybe you'll be inspired to start your own company, which several of alumni have done.
Join us. If, like us, you're passionate about how things work and using that knowledge to design and build products and applications, then engineering science is for you. To learn more, you can visit our website. If you have more specific questions, you can reach us by email or phone. We look forward to seeing you.
Thank you very much. You don't have to reach us via email or phone. You can ask in the chat. I'll continue. So that was a brief overview of ESP or engineering science. And we'll continue now with a slightly more detailed presentation. I'll not talk for too long, I hope. Let's see. Joshua, can you see? The slides?
Yes, yes.
Perfect. Let's go again. Now, what is engineering science? You probably have heard about mechanical engineering, chemical engineering, electrical engineering, but perhaps less so about engineering science. Now, if you look at Singapore, it is relatively young. It launched in April 2006, the engineering science program, as a flagship educational initiative at NUS. We have a student intake of around 40 students per year. And our mission, if I really narrow it down, is to fulfill Singapore's need for a new class of engineering scientists who are better prepared to solve multidisciplinary engineering problems. So the key word is really multidisciplinary, develop innovative designs, integrate systems, and work at the interface of disciplines. How do we achieve that mission, that multidisciplinary mission? It starts with our teachers from 2 colleges, from agencies and industry. You can see colleagues here from electrical engineering, physics and chemistry. We have mechanical engineering, for example, and we have from agencies and industry, all coming together and teaching, all of us bringing our own experiences from around the world and putting that in context, multidisciplinary, so in ESP. Our student-teacher ratio is around 10:1. So per 1 professor, you have 10 students, which is really good. We can have this personal connection with our students. Some curriculum highlights: we have hands-on small class experimental modules combined with interdisciplinary core modules in science and engineering. And what we really strive to do is to bring the theory, which can sometimes be dry and abstract, to life in our laboratories where you get a hands-on experience. And for this, we have 4 labs. If I start with the Faraday lab to the left top here, here is where students work on sensors. For example, they study buckling phenomena, heat transfer, for example. In our design studio, left bottom, students work on green buildings, on various sensor systems, advanced air conditioning systems, for example. They design, work with these hands-on. In our multidisciplinary lab, shown here to the right top, you can work on nanodevices where we employ a bottom-up approach where you grow small units into nanostructures, as an example. In our nanofabrication lab at the bottom here, you can get to work on lab on a chip, for example, or you can grow nanostructures with a top-down approach where you break down bigger structures into these nanostructures. So that, in a nutshell, is a curriculum highlight for our labs. In addition to that, in the first 2 years, which are really strong in fundamentals in particular, we have 4 specializations, and we've had these for a long time. We try to keep 4 specializations. We have nanoscience and technology, starting from the left, where you work with everything at the nano scale. You have computational engineering science, where you can work on AI, robotics, simulations from the atomistic all the way up to the continuum level. We have energy science and technology specialization, where you can work on renewable energy, say solar, fuel cells, batteries. Sustainability is an important topic. And we have engineering science and medicine. And we heard a little bit from Rachel in the video. And in particular, physics and imaging is a strong element in our engineering science and medicine specialization. Besides the specializations, you also have an option to really tailor your own degree when you go into ESP, the engineering science program. And here are 5 examples that I've shown you. You can see at the bottom, we have the common curriculum, which all students that go into CDE, the College of Design and Engineering, take. On top of that, you have an orange, the major, which is the engineering science program, where you have the strong multidisciplinary flavor to it. And on top of those obligatory blocks there, you can now add on a little bit depending on your interests. And 5 examples, as I mentioned. One is where you pick a specialization in engineering, science, and medicine, and you do an additional minor in public health, for example, to make you more attractive and make you stand out when you start applying for jobs, for example. And here you could aim for a career in medtech applications. Another example is if you go for a specialization in energy science and technology, and you pick a minor in management, you could work towards a career in corporate sustainability, as an example. If you, in the third example, you pick computational engineering science as your specialization, you could go in and do a minor in mathematics. A number of our students in the past have done so. and you can look at a career in defense, for example. You can also pick 2 specializations from ESP, not only 1, but 2. And here's an example of energy science and technology specialization and computational engineering science. And now you could go into career in energy and automotive technology as an example. Or besides taking the major in engineering science, you take another major, for example, in statistics, if you are very interested in mathematics. Then you can look at a career in data analytics. We're also exploring options where you can do a double degree program with physics. We're also exploring options for working with physics more closely, and there will be a number of overlaps in terms of module where you can double count modules, which will make it easier for you to take, say, a second major or a second minor or first and so forth here. So lots of opportunity here to build your own degree. Besides the curriculum, since ESP in Singapore is rather young, we have worked hard on establishing a partnership with universities around the world that are strong in engineering science. Engineering science as a topic, as a concept, has been around for over 100 years in other parts of the world. And we now have an international consortium together with a range of universities. Giving you a list here, for example, Cornell University, USA, KTH from Sweden, where I come from, Osaka University, Japan, University of Toronto, Canada, for example. And this partnership, this consortium allows us in ESP here in NUS to provide more opportunities for student exchange and experiences if you join us in the engineering science program. And on that note, many of our students do go on student exchange programs. I highly recommend it. If you go abroad, you demonstrate that you can live and breathe in a different culture, you can work there. That is an excellent experience, and that could help you in your future career as well. And here is a sampling of universities that our students have gone to for student exchange programs. We have University of British Columbia, for example, University of California, Toronto. So you can see a mix of our consortium universities as well as other universities popping up. We have ETH Zurich, for example, IIT Bombay, Tokyo Institute of Technology, University of Auckland, National Korea University. So a range of universities that are open for our ESP students. In addition to that, besides our hands-on curriculum in ESP, we also have the internship where you go out to companies, universities, and research institutes, and you work with for around half a year on various topics. And this is an additional kind of hands-on experience, I would say. And again, a sampling of companies that our ESP students have gone to. You can find Access Engineering, you can find the Norske Veritas, DSO, Global Foundries, Phoenix Solar, SD Engineering, for example, universities, Toronto, Osaka, our consortium here, and research institutes, for example, Institute of High Performance Computing. I did my postdoc there, or Solar Energy Research Institute in Singapore. So a wide range of options where you can do that internship and explore working life a little bit and explore your interests. Now, once you're done with our program, you'll go out, you'll either go out and start working or you go for graduate students. And many of our students, they find jobs, all our students, I should say. So they either they start working after graduation, they go for further studies. And our students find jobs in a wide range of industries and companies. And here is again a little sampling. We find Micron, Schneider, ABB, Schlumberger, Global Foundries, REC, Siemens, Procter & Gamble. So our students go to a wide range of companies. They are not limited by, say, being an electrical engineer or a mechanical engineer or such, because they will have this multidisciplinary nature. They will have a blend of modules in our core curriculum that span mechanical, electrical, physics modules, and so forth. So you will find our students in a wide range of companies. So we are trying to prepare you for a lifetime of different careers, not only one career, that's in the past. Now when you graduate, you really have to be mobile, be a quick learner, and adjust depending where the job opportunities are. So as I mentioned, besides finding jobs in different companies, many of our ESP students also go for graduate studies. And we can find, for example, Yale, Harvard, Caltech, Duke, NUS, Stanford, Georgia Tech. Now, perhaps most importantly, to demonstrate the success with our multidisciplinary program that we have in ESP is, if I zoom in on NUS and we look at where our ESP graduates have done their PhD, you can find that they have done a PhD, some of them in biomedical engineering, some in chemical and biomolecular engineering, electrical and computing engineering, mechanical engineering, material science and engineering, and in physics. If we go to Stanford, we find applied physics, for example, Harvard, applied mathematics. So you can see that with the strong multidisciplinary nature, strong foundations that you will get with us in ESP, you will be able to further explore. And this also means that you don't really have to decide first year now what you really are interested in. You can explore it as you go along with us. And if you're interested, you can then go for graduate studies. Now, you might ask yourself, Eric, this all looks fine, but how well are they really received? Aren't they jack of all trades? You say that they do electrical, mechanical, physics, that they get a strong multidisciplinary foundation. What about depth? Well, we do have those specializations, for example, but regardless of that, let's look at what industry pays the graduates. So I take that as a benchmark of how well received the graduates are from a program, and that is how much is industry willing to pay our fresh graduates. So within roughly 6 months after graduation, what are the starting salaries? And you can see here from the 2021 Graduate Employment Survey, draw your attention to the y-axis. Here we have the mean gross monthly salary that graduates have commanded from NUS. I'm only showing you from NUS here and from engineering. So these are the programs from engineering, mechanical, for example, engineering science highlighted in red. You have chemical and biomedical engineering, and you have Bachelor of Science and Bachelor of Science honors to the right here. And draw your attention to the red bar. This is where engineering science is at. And you can see that we are among the top ranked when it comes to starting salaries. Now, let me try to summarize everything I said into why you should pick engineering science and why you should study with us, why I strongly recommend it. And the first point here is that you will get a strong scientific fundamentals in cutting-edge engineering applications. Again, strong fundamentals that span disciplines. We are not bound by electrical or mechanical. We walk across disciplines. We look at those fundamentals that are of particular interest and value, and we combine that with our hands-on design projects where you will get hands-on experimental confidence. We'll work with our staff, passionate staff, I promise you that, and work on these with your peers on your design projects. We are multidisciplinary, preparing to work in several disciplines and at the interface of these. And I believe looking at the statistics, for example, the starting salaries, this is where ESP graduates are really strong. You're not, again, bound by one discipline. You're able to speak electrical engineering, you're able to speak mechanical engineering. Typically, different disciplines have their own language, and you will be able to walk and speak those languages. In addition to that, to allow this mission, we keep our student numbers small, around 50. Why do we do that? Because when you interact with a large class, say hundreds of students, it's completely different as a professor to engage and connect with the audience, with the students, compared to having a small class of, say, around 50 students. That personal style of education allows us now to impart all of these fundamentals as well as the hands-on experience. Now, please don't worry about the small number. We are flexible. If more apply for engineering science, we can stretch these numbers. So please don't worry about that you should have smaller chances of getting into engineering science. And I've already alluded to this. You were able to freely interact with your class professors and get to know them personally. I think this is really important. With a student-staff ratio of 10 to 1, so again, 10 students per professor, you'll get to know your professors. And if you're interested in the research topics of your professor, for example, you can have an undergrad research opportunity program with that professor. You will have your own mentor. And let me give you two examples. Ignor, our alumni, is going to talk a little bit more about this, but I thought I'll bring up two more alumni. On the left-hand side, you can recognize perhaps Rachel from the video. She did her specialization in the biomedical specialization. She's now working in an A-star. And this is from an earlier design project that she did. Going to the right-hand side, we have Raghav. He's now a head of project management, Clean Tech Solar. And I still remember him from a module Transport Phenomenon and Energy System 2012. And he gave a fantastic 1-hour lecture, because in that module, I videotape students as they give their lectures. And it was absolutely fantastic. So what happens is, with this personal connection where we as professors, we remember our students, we worked very tightly with you in our classroom. We can write recommendation letters, not only at the moment when you graduate, but later on as well. And that brings us to the end of this short presentation. So if you're passionate about engineering and science, do consider joining us. You'll find more information on this slide here. And with that, I'm going to end my short presentation. And what I thought I would do now, so please, you can use the chats, ask any questions in the chats, and we will try to answer them in the chat. And then afterwards, we can then have a Q&A session as well. So I thought the Deputy Director, Jerome, could talk a little bit more about our design projects. Very, very exciting stuff, a little bit maybe about our research. And once Jerome is done, I'll pass on the word to Ibnur as an alumni to talk a little bit more about his experiences. Jerome, over to you.
Thank you, Eric, for this nice introduction. I am the Deputy Director of the Engineering Science Program, and as mentioned, is a very unique program. It's the lectures are not only from CDE, but they're also from colleagues of humanities and science. I'm a physics lecturer, so let's have a look. What is engineering science about? Actually, engineering science started in Switzerland already in the 1800s. In the Technische Hochschule in Switzerland, there was a school which was a combination of engineering and sciences. So engineering science is actually is very old fundamentals. But let's have a look at a very famous physicist, Richard Feynman, and he is saying, nowadays electronic circuits, this is already actually before the electronic circuit started, he was already thinking way ahead of that. He was thinking, when people start at some point soon make the circuits, can we not do better? And he was even proposing, can we not use the energy levels within the atoms and the quantized spin within the atoms? He was really way ahead of his time. And at the talk, there's plenty of room at the bottom. He was also talking about making small machines that can make our gadgets, which we now have realized, of course, with all our integrated circuits. But let's have a look at his other prediction. Actually, in 1998, Kane proposed exactly what he was asking. He proposed, let's use two silicon atoms and see whether we can use the spin levels of these silicon atoms to do quantum computations. And it still took quite some time, but now, if you want, you can actually rent time on the IBM quantum computing system. There's only a few systems around the world at the moment that are running, but you can rent time on these systems. And they have to be cooled down to very low temperatures, but they can possibly provide breakthroughs in the next coming years. The question is how long, but people are working on it. And as I mentioned, the first part, people are making integrated circuits smaller and smaller. We're all familiar with that, with our phones and PCs. But on the other hand, on the bio side, you have your standard bio lab where people do analysis. Wouldn't it be better or nice if you can do this all on a lab on a chip device? We nowadays have our COVID test. You just throw a little drop and then you know your results. Here's a bit more complicated example. Sorry. So let's have a look in a survey of American universities and industry, what they perceive as being very important. We see here biomanufacturing, biofuels, materials genome. We know with the COVID, it's very important to understand this. Industrial robotics, mobile robotics, self-driving cars, for instance, and then zoom in to the top. Advanced sensing, nano manufacturing, information technology, nanoscale materials, energy efficient, visualization. You see, all of these are actually captured in the specializations in the engineering science program. We really positioned ourselves at the forefront, and we give you a degree which is really can help you lifelong going forward in nowadays society. Just a recent investment by Singapore in the so-called SG 2025 plan enterprise by the National Research Foundation and the Prime Minister's office. They now are going to invest 25 billion in from 2021 to 2025, an increase of 31%. Actually, normally I like to put the American investment, but actually Singapore invests even more than America in this plan. In the National Nanotechnology Initiative, they only invest for 1 year, 2021, 1.7 billion. Singapore is investing 25 billion. Okay, this is Singapore dollar, but still they're investing a huge amounts in this area. And that goes to manufacturing, health, urban solutions, smart nations, and so on. And there again, you see again the specializations which are in the engineering science program. Here I show a little bit of my own research. I work in the physics department in the Center for Ion Beam Applications. We are developing very novel imaging and nanofabrication technologies where we can make very interesting devices which could possibly help to improve imaging in wafer fabs, and also possibly help to make what we saw earlier on the quantum computing systems. They have to be cooled to very low temperatures, and it's huge systems. If you could use our system to make these quantum computers in different materials, we could possibly shrink them so they can come to your own phones, possibly in the near future. And another thing that we do is we work on DNA nanofluidics, where we can look at genomes, which can be used for many disease detections. So we collaborate a lot with Singapore industry and hospitals. I would like to now highlight a few major design projects which work on soft robotics, harnessing of light, and they are typically in collaboration with different companies. The recent companies we collaborated with are mentioned here. Lumiled, by the way, they are the largest producer of LEDs in the world. Helios is a very interesting company that also does a lot of interesting engineering solutions for the Singapore industry. So let's have a look at the lab where we do this. We saw just now a picture of the lab below here, the SIBA ESP nanofab fabrication facility. Behind it, we have actually a clean room facility, because if you want to make some of these devices, you need to work very clean. That's behind here. Here we see one example where we can possibly separate nanoparticles very accurately in chips we have made. Here we see some of our machining capabilities which we use in our lab practicals. And we see here a mold which we can use, and I show this in the next video, for making soft robotic devices. That is very applicable, because if you want to make, for instance, COVID vaccine, you need to handle samples very delicately and with very soft touch. So let's have a look at this in this next coming video, where people in this third-year laboratory made something that can pick up a very soft device, in this case, a grape. You don't want to squash the grape. So look, they made this. They made everything. They made the self-clamping device, soft touch, the interface, the robotic handling. It's all done in the third-year laboratory, lab practicals. To give an example, but I don't have the video on that. In the second year, you make your own scanning tunneling microscope. It sounds very exciting. It is very exciting. And some of the seniors actually told me, if through our lab practicals, we really understand how complicated machines works, and I can run a factory much better. Let's go to the next video. And here we see that we can actually, with a tracker, a laser tracker, through artificial intelligence, only track balloons. We see here Nicholas, the laser only follows the balloon. And if he puts another ball, the laser doesn't go there. Because through his artificial intelligence programming, he will only track the balloon. So this is very, very important for many different types of applications. So I have one more very exciting project, a so-called sorter. It's a Lego sorter. It sounds like helping your parents if the kids have made a mess of the whole play. With the toys, but then you can have this system that can actually sort out the different Lego colors and sizes. You would think, what's the point of this? If you have all your blue baskets outside and you throw all your garbage in, you just reprogram the recognition. We saw just now recognition of balloons, but in this case of Lego bricks, you can do garbage sorting, and then this system could do the sorting for you. Nanotechnology. I just would like to give one more outlook, because I'm in the nano specialization. Nanotechnology is now in the state where computer technology was 40 years ago. As I mentioned, if we can come up with a method that can revolutionize the way we make quantum computers, for instance. Just now we saw that was in silicon. You need huge machines. They each weigh several hundreds of kgs, and that takes a lot of manpower. If you could make it in different materials, you could actually shrink it, if you make it in diamond, to, as I mentioned, something that can go in your handphone, for instance. That would, of course, be really revolutionary. Here we see some companies we saw already before. I will not highlight the left table, but here are on the right some other companies with which we collaborate. And recently I managed to get some internships for ESP students to work in wafer fabs, for instance, or in Rapiscan. That's a company producing X-ray systems that work security scanning in airports, for instance. And Hexagon, as I mentioned, that's a company that come up with engineering solutions. They, through artificial intelligence, possibly can replace or the way people make airplane wings, for instance. They can make them much more reliable, and through artificial intelligence improve this type of fabrication of airplane wings tremendously. They have already contracts with Boeing, and they're working on contracts with Airbus. So with that, I would like to end my presentation and hand over, I think, the floor to Ibnor. Thank you very much. Let me stop sharing.
Thanks so much, Prof. Yeah, so it's hard to follow after two amazing profs, right? So my name is Ibnor. Hopefully you all can hear me. Yeah, okay, very good. Yeah, so I was from the pioneer batch, right, of the ESP program. So I'll be very honest with all of you, right? Before engineering science, I was actually wanting to become a doctor, right? So I went to apply for medicine, and I went through the interviews, and I felt a bit demoralized when I wasn't given a spot in medicine. But then I started to explore what other alternatives there are, and engineering science emerged, right? And that was the time when I was still doing my national service, figuring out, right, what is the future of the industry, and then what would be my contribution to that future, right? And I think a lot about what Prof. Eric and Prof. Jeroen has shared earlier. It's about being ahead of the time is very important. I think it's something that people don't realize. I'm actually very fortunate to have gone through ESP program, and now everyone's talking about sustainability. If not for engineering science program, I would not have even explored sustainability in a scientific and engineering manner, right? And because now a lot of solutioning for sustainability, it's beyond activism, it's beyond having campaigns. A lot of it is about inventing new solutions, which I'll be sharing some of the sustainability inventions which I work on, and that has been my passion. So invention, ever since ESP, invention has been like the thing I've been working on. And a lot of the skills, right, required for inventing things in a team is something that you will get to experience when you're doing your design project. Right? How do you navigate different conflicts, different ideas, different problem statements? How do you manage the expectation of the stakeholder? How do you turn their expectations into specifications and measurements, right? That will translate into the material selection, the computational simulations that you need to do, right? All those skill sets are super helpful for me and my team today. So also in my team is Ihan, which is another ESP alumnus, right? And yeah, yesterday we had a program with students, and they are from the low income community, right? So we made them experience how to build our invention, which is a floating farm module system. And we let them experience a bit of physics by launching water rockets, right, into the sky. So these are things that we are doing in Guild, which is the company which I run, and a lot of the focus is trying to bring that spirit of science, engineering, mathematics, right, into the masses, right. I think that's something that we want to hopefully nurture in the younger age. So maybe in the future, right, they will become ESP, part of the ESP students as well. Right, so I'll quickly share my slides right over here. So a lot of things that I work on at Guild is something what we call thinkering, and I think it's a lot. It's exactly what ESP is all about. It's about thinking, and then you tinker with things, right? And then we start to realize that in the tinkering, in being hands-on, you actually start to think a bit deeper about the things that you need to work on, right? And a lot of the intersections that we work with in Guild, it's on nature. So some of the challenges that we were, again, ahead of our times back then was on agriculture, right? So not everyone's talking about food security, but upon graduation from ESP, also thanks to the experiences from NOC and some of the Mondialogo engineering project, which we work as part of our, extracurricular activity during ESP, that influenced us to look at food a bit more seriously early, right? So a lot of the things that ESP wants to kind of like nurture you is to start to think ahead of the curve, so that when the curve finally arrives, right, you are somewhere well positioned for it, right? So the difference between what Guild does and a lot of the other non-profits is that we have a tech angle to it, right? And I think this is a lot to do with the ESP upbringing, and also our belief that tech helps to amplify change, and we work a lot with community. Yeah. So the idea of being a thinkerer, right? So basically I invent. At the same time, I also work with communities to build solutions, right? So for example, yesterday we were with low-income children. On a different day, I'll be 3D printing something for the blind community, right, with my designers. And also because of COVID, a lot of the adults, right, were retrenched, all right? And basically I was being asked by the SG United program to help curate a whole curriculum for something called the Robotics Process Automation, or RPA, right? And the idea is to bring back engineers who were displaced during COVID to enter something called the RNA sector, or the robotics and automation sector. So in that perspective is to prepare them for something called the Industry 4.0, right? So essentially I'm kind of like quite blessed, right? That I picked up like C programming from Prof. Eric during university, and that helped me to train up the engineers, right? The adult engineers as well. So a lot of things that we want to kind of like think about. It's not just the engineering science skills, but also the other the soft skills, the transdisciplinary, the cross-disciplinary aspect of things, and that's why we realized that even for the adults, right, those who were more easily displaced, right, they have what we learn about their history is they don't know how to work in team projects, right, and how to communicate their ideas well, right, and these are things that you will definitely have to go through when you work with design projects, and you rotate your teams, right. So it's a very good simulation of the industry, right, if you go through the ESP program. So what are the three things? You need to be a good inventor. So these are three things which I've been exploring, right? Ever since ESP, even till today, it's the idea that you need your brain, right, which is your head, and you need your hands, right, and last but not least, you need your heart, right? I think these are three things which I hope to nurture and also learn from others, right, as well. So my journey is quite complicated, right? So it's not straightforward. Upon graduation, I immediately joined a MNC or government service. Though I was offered to join Google, pardon my cat, things that happen during working from home. Okay, so okay, Silver. Okay, I'm here. Okay. So I went to the Housing Development Board as part of an engineering internship program, right? So this is something which I learned, and at that point of time, we were already looking at solar panels. So again, about being ahead of the curve. In 2007, 2008, you're already looking at solar panels, and now you see it in mass implementation across Singapore. Right, I was also part of the NOC program in Stanford, right? So working in a startup over there, in a mobile payment startup. And then when I came back, I did a bit of healthcare policy and innovation studies in the Lee Kuan Yew School of Public Policy, right? And that's when I started to see the intersection between what I studied in ESP and the public policy sector, right? So even though if some of you may consider a role in public policy in government service, ESP is actually a very good starting point, because later when you enter government service, you realize when they start to talk about digital governance, when they start to talk about things like cyber security, right? These are things that you will need to have some form of fundamental, right, and foundation, and ESP provides that. In 2016, that's when Guild got formalized as an enterprise, and along the way, I had a chance to do a kind of an apprenticeship in ST Logistics to look at innovation in the logistics sector. And later on, through the Robotics Automation Center of Excellence, that's when, which I shared earlier about training up the adults, right, into joining the robotics and automation sector. And there's this thing called the Floating Gardens Initiative. So this is the invention which we created, right? And it's something to look at growing food when we have a lack of land, right? We use the water surfaces as our place where we can grow food, and thankfully that has been awarded a gold award internationally as well. Simple invention, but it has impact. All right, and we saw the outcomes of growing food on our Chinampa during COVID, when no one could water our plants, or when no one could actually water plants, our plants survived, right, during the circuit breaker because of our technology. So the journey has been varied. The experience which I had, so this was at Silicon Valley, right? Quite a number of ESP seniors, alumnus, went through the NUS Overseas College program as well. So some of you may want to become entrepreneurs, you may want to start your own businesses, or even join a startup after graduation. So the NUS Overseas College was a good exposure for me, right? And having the tech background for ESP helps a lot. The question which I often work on almost on a daily basis is about this paradox, which I'm about to share, is the idea that economically speaking, right, we have millions of dollars, right, or even trillions of dollars moving around the world today, and we have like the best technologies, right? We have a lot of leaders, right, giving promises. Having said all this, right, we still destroy our environment. We still create so much trash, right? We couldn't feed even 1 million people with proper food and nutrition, right? And this is what I call the going bananas equation, right? So you have billions of dollars, billions of promises, but somehow we can't alleviate, right, poverty or inequality or even suffering, right, of billions of people. So the idea of using engineering and science for change, or engineering and science for impact, is something that I've been working a lot on after graduation, right? How do we bring this to impact people on the ground, people in dire situations, not just in Singapore, but also overseas, right? And And the three kind of the skill set which helps, right, in achieving this, it's curiosity, right, creativity, and grit. And these three things, for sure, you will go through it in ESP, right? You will be asked a lot of questions, and you'll be encouraged to ask a lot of questions and ask why, because you are at the frontier, essentially, right? Even people globally might not have the answer to it, right? So that curiosity is super critical. And the idea of having design project, it being open-ended as well, encourages you and nudges you to be creative. I still remember one of the design project was to identify a Wi-Fi beacon hidden in NUS, right? And literally all of us had to build our own antennas from scratch, right? And my team literally went to the music van, we went to find walks, right? We find wires and we made our own helical antenna, and we kind of find that the beacon. And I think that was very, very insightful as a whole experience, right? To turn DIY, your maker skill, right, to build something to solve a problem. And last but not least is grit, right? And I think this is something that we will experience. ESP is not a very easy, to be very honest, it's not a very easy subject. Having said that, it is supposed to prepare you for industry and it's supposed to prepare you for the frontier, right? And even when you talk about like astronomy, space, right? Things like that require you to have a level of resilience and grit, right? To go through that, and ESP will prepare you for that, right? When you see your experiments fail, you have to think about, okay, what's the next thing, right? Can we learn from that failure, right? The experience that I had during ESP was something called the Millennium Development Goals, the Mondial Logo project. So this was during my year one or year two, right? When a few of us came across an email in the spam folder about United Nations asking for engineers to work on a United Nations problem, right? So I remember at that point of time, we wanted to work on a solution related to healthcare, and then later on we decided to work on food, right? And specifically on drying, right? So this is something that it started from an idea, and then we start to collaborate with universities in India. Right, we went to the villages. So as you can see over here, this is Hui Ming, right, who's also a staff in ESP, right, and we built up a solar dryer project, which over the years, right, till very recently, last year or the year before, it got the DBS grant, which is a huge grant, right, to alleviate poverty in villages, and it's being championed by women entrepreneurs, right? So now they are using the solar dryers, right, in the villages to dry their fruits, and now they are selling it. And I tasted the food; it's great, right? And that's when we start to see innovation being used effectively, even in, I would say, low-tech environments. Yeah. So yeah, we got gold for that, right? And a lot of things at Guild, it's about putting your thinking and that maker mindset, right? So we are very into the maker movement, right? And the idea of launching it out to the real world is something that you will experience when you do your design project. You cannot escape from that, right? You have to make a solution, right? And why we look at nature, technology, and community, it's because, right, the core belief that nature, it's about the planet. That's what our lives depend on. That's where we get our resources. Technology, that's how we make things work, and community, right? So I will kind of like quickly show I want to show specifically this one. So this is the IBAM, right? The IBAM design, where is this one? So the IBAM is one of the inventions, right, that we created. And what this does is essentially amplifies music without any electronics, right, without any electricity. And how this is being designed, there's actually physics to it. So it's a resonating chamber, right? And I think this is something that I learned in, I think, mechanics and waves class, if I'm not wrong, during ESP, right? And kind of like figure out what's the correct dimension, right, for the sound to be amplified beautifully, right? So this is one of the inventions, right? That this is one of our customers in France, all right? So she bought it. So it's a global invention. The other one is called the Floating Chinampas project, which is this one, which I'm holding here. So the idea of the Floating Chinampas, it's inspired by the water hyacinth, right? And some of you may have heard about the term biomimicry, right? Again, I learned about biomimicry when I was doing nano, one of the classes on nano. I think it was an optics class, and I wanted to do a literature review on structural color, right? And then some of the scientists around the world, they were looking at butterfly wings, right? And how butterfly wings at the nano level, when they use imaging, they look like Christmas trees, right? And that got me excited about biomimicry and how we can learn from nature to create inventions, right? So when I was looking at the water hyacinth and the ability for it to float, right? It kind of like got me thinking, like, can we float our farms? Can we float our food, right? And how the water hyacinth is getting their nutrients is directly from the water. So I'm not saying that we build like a floating structure, right? Maybe made up of like cement and then or even a plastic layer, but it separates the water from the growing medium, right? So I'm looking at something that's a bit more like water hyacinth, right? And that's how the floating chinampas invention got created, right? So over here, this is iteration number, I think it's number 23 or 25. So this has gone through like many iterations. Again, a skill set that you will learn when you're doing your design project in ESP, right? You have a failure, you iterate, improve on it. Again, you refine it. You have another failure, you improve on it. So the earlier prototypes we had like our farms sinking, our vegetables dying, right? So this is like more successful one, right? And the idea is that these are actually water bottles, right? So the initial idea was to literally create farmland like reclamation, right? We put like mud and soil from the base of the lake, right, to the top. And that's called chinampas. So it's an ancient technology. You can do your own Google research. Chinampas is an ancient technology which they practice even till today in Mexico, right? Where they reclaim all the way to the top. But what we realized is that now we are in modern society, we have too many plastics, right? And what if we use the plastic bottles, right? Preserve the integrity of the shape and arrange it in a way that it can hold the structure, right? A floating growing medium, and the substrate in the middle. So it's not like pure hydroponics. There's actually soil right in the middle. Then the next natural question, which we were asked by the Japanese judges, right, when we were exhibiting this in Taiwan overseas, right, in an invention competition, the Japanese judges were very sharp, right? So they asked questions like, so you put soil, wouldn't the soil immediately go into the water, right? So there are certain things that we do with regards to the substrate, right, to hold it in place. And we start to grow things, and what we observe is that it grows way better than on soil. And most recently, earlier I saw a slide on corporate sustainability. So we are working very closely with L'Oreal. I know L'Oreal look at cosmetics, but they are also interested at looking at biofilms, right? So they are looking at our structure as a possible, like a biofilm growing under the structure that we built, right? And the roots are huge, right? So here you can't see the roots, but if you were to pick up an actual floating chinampa, you will see a huge amount of roots. And what we discover is that not only can we grow food, some of the plants can actually extract chemicals, right? Including radioactive chemicals, like things like uranium even, right? So these are things that we are beginning to learn about plants, right? And how do we incorporate, this is the science part of things, right? Which is the chemistry, the biology, and then the physics of it, right? Which is the engineering part, right? Which is looking at the how to make it float, right? How do we even incorporate sensors? So I have another team that is looking at using IoT, right, to kind of like measure the moisture level, the acidity, right, using sensors, right? So these are things that we work on a lot at Guild. And again, a lot of these skill sets are something that we learn back in ESP, right? So I think we'll end over here, right? I think we can take on some Q&A if you have any questions. Alternatively, you can also find me on LinkedIn, right? You can find Ibnor, right? It's not a very common name, yeah. And I'm happy to share with all of you what we have gone through, and maybe if you have certain ideas you want to explore, to prototype or to tinker, to test with the community, we are open to that. So thanks so much for the opportunity.
Thank you, Ibner, for your fantastic talk. I really loved it. I'm thinking that we stop with the presentations and give you guys a little bit of time to ask questions in the chat, and we'll try to reply to them. And maybe in a few minutes, depending on the number of questions, our two ESP students could talk a little bit about their experience. And be honest, don't worry about me. I'm so you can talk a little bit about your experiences. But again, let's have a little bit of a break and ask questions in the chat if you wish. I think Ibnu came in very nicely talking about soft skills and the plethora of skills that you're going to pick up with us that complements the engineering science, the hardcore skills. That teamwork in design projects and working late into the night, sometimes debugging, motivating your peers, pulling everyone in the same direction. And we like to rotate group members, for example, in different design projects. That's the whole idea. We wanted to work with different people and for you to learn how to work with others. All very important soft skills. Let's maybe take 1 or 2 more minutes. I'm looking at the chat. What you can do is you can ask everyone, or you ask individual speakers if you want to as well, if you want more, if you don't want everyone to see your question. You have 2 options there in Zoom.
I believe they can also unmute, right, if they want to.
Yeah, oh, of course, absolutely, yes. All right, I'm thinking, can we hear a little bit from Tawakkul and Jaren? What are your thoughts? Because you're going through ESP right now, so maybe you can give that little bit of, what is it like to take engineering science? I pass over the word to you two.
I can go first. So hi everybody, I'm Tawakkul. I'm a year 1 student right now. So if you are interested in engineering science, you'll be doing the same curriculum as me. So the curriculum got revised last year, so I'm the first batch. So I can talk a little bit more about it. I think as like Prof. Eric described, there's a lot of flexibility in what you can do. Literally, like you can come in and like on top of your ESP major, you can choose a lot of things. So I got friends doing physics, quantitative finance, philosophy, right, Prof. Eric? Yeah, so it's really, really exciting to come in knowing that really, like the world is really, like you can really do whatever you want, right? But I think I'll talk a little bit more about student life, okay? So I think what I love a lot about ESP is the fact that it's deliberately kept very small. So the fact that it's kept very small means that you really get to have a lot of interactions with everybody. You know everybody, everybody knows you, you know by face, you know by name, and you get to like forge more meaningful friendships, you know, and at the same time, when you work in group projects, you are working with people that you know. So it's just better in that way. Also, at the same time, the cool thing about ESP is that because we're small, we can have physical classes. So again, you know, you can have interactions with your professor, and the professor in ESP are all amazing, by the way. Super funny. Like currently I'm being taught by, yes, super amazing, super funny people. I love them a lot. Yeah, like my current professor, Prof. Anjam Khurshid, he is a super amazing guy, and yeah, he's funny, he cracks jokes all the time. So it just adds to the whole learning experience. Yeah. On top of that, NUS in general, right? Like student life in NUS, for lack of better words, it's super colorful, it's vibrant, it's exciting. You know, there's so many CCAs. Literally, if you have an interest and a passion, there's probably a CCA for that. I'm pretty sure there is. If there isn't, you can create one because NUS loves like student-led, student-initiated projects. For me personally, I stay on campus. I stay in the RC. I think Jaren also stays on campus. So campus life too adds to a meaningful experience. So yes, do apply for campus if you can. Yes. Yeah. But yeah. Yes, Jaren, you want to say anything?
I guess I can talk more about the lesson structure and stuff.
So I guess like in ESP, you start off with modules that are more difficult than others. And I think at the start, you don't really know why, but I'm a year 2 student and I'm starting to slowly appreciate why the modules are so intense. Because when you get to your design projects, everything falls into place. Like you look at a formula you have learned in year 1 and go, oh, that's how you use it. Like, oh, I see now why they've been so, the professors keep telling us that, oh, this thing is quite important. And I think the best thing about ESP is that all the professors are quite knowledgeable. They can talk to you days and days about the thing they are passionate about. You can go out and talk to them about anything. So like, I have friends who are interested in like biomed and they go on to find professors in ESP to do research projects with, right? And I think that's one thing that's important in ESP. Like a lot of my friends in Mac Eng and stuff, they don't really have that connection with the professors. It's a lot of like, oh, I come for lectures. The lecturer teaches me and okay, I'm done. I'm going to go back to study. But in ESP, you can stay back, and because it's like 50 people in a class, you can go up to the professor in a group and then you all can talk about the things you have talked about in class. And it helps build your understanding and stuff. Yeah. Do you have anything else? Aku?
Thank you so much. I did not pay you to say anything of that. Very happy to hear. I think we try to be a little bit, since there are so many fundamentals, we want to cover quite a bit. That's where the intensity comes in, I believe, in ESP. And that's a good thing. And Ibnur spoke about that a little bit in terms of grit and all those skills that come into it. Great, thank you so much. Let me see, I'm looking at my chat now. Anyone who wants to say something, please feel free to do so. Oh, there's a question here in the chat, whether you will have exposure to these specializations already in year 1 and 2. And the way we do that is we give specialization talks. We just had one where the colleagues who teach, we have 4 specializations, we pick them and they give a talk, one after the other, and they talk about the various projects that you have, the various modules. They talk a little bit about employability, the kinds of jobs you can get. And again, we just had that specialization talk. Year 1s and year 2s were invited. And after I looked at my colleagues, I want to take all 4 specializations. So please sign me up. There's really, and what I realized from those specializations is that even though we have 4 specializations in ESP, there is quite a bit of multidisciplinary overlap between these. So even if you only take one specialization, you will still learn. So if you do energy, for example, there's so much nano inside. Fuel cells, batteries, solar cells, you can go down to the nano level at the fabrication process, for example. Same with biomedical specialization and computing and the computing specialization. So there's beautiful overlap. And the way we do it is we expose you. We have these sessions where we talk about it. I also recommend talking to your seniors. That's a good thing about ESP, again, because we're not so many, it's easier to network. You're not overwhelmed with it, with a number of students. And hopefully when things go back to normal, we'll have our barbecue celebrations, we'll have a mooncake celebration, and you can interact with your seniors, get feedback, thoughts, ideas from them as well. So it's when it comes to specializations, after the first 2 years, you're going to have a pretty good idea, I think. And again, if you pick a specialization where afterwards you say, maybe not my thing, we have to see that the specialization is limited. It's 5 modules here. So to me, you're not defined by a specialization. It's something that where you're passionate about something, you go into that specialization. It gives you an edge at a job interview. But if you pick energy specialization, that doesn't mean that you have to work with energy for the rest of your life. That is not what engineering science is about. It's about all these fundamentals from mechanical, electrical, and so forth, and being able to job hop, finding those opportunities out there, and even within the same company, being able to take on different roles, for example. That to me gives job security, and it gives you that flexibility with, as I mentioned earlier, a lifetime of different careers. Not, if I look at my parents, they had one career. Okay, I'm also having one career, but I'm enjoying this so much. But there really has been a change towards everyone having to be able to adapt and adjust and looking at different careers, not only one inside.
Actually, building
That's
up on Prof, right? You were saying about having multiple careers. So like when I'm with the SG United adults who are recently retrenched and trying to get back into the service, right? We start to realize it's important to have a kind of a jack of all trades layer, and then a master of three, right? So three different skill sets, right? In case one of the industry collapse, you still can go for the other two. And I think engineering science, having engineering, knowing science, and having a specialization, right, could kind of like help you cover quite a safe base, right, if you need to navigate into the future. And true enough, some of my kind of like same classmates, right, from my batch, right, some of them are in Ninja Van, right, having an important post over there. Some are like in Philippines, right, kind of like championing some of the like Zhihan, right, at Vivagosphere. So I think that the having the misunderstanding that people usually have is that, okay, so we are a jack of all trades, master of none. But I would say we are master of at least one, right, if not two or three. Yeah.
I think when I look at where our graduates start working, they take traditional electrical engineering jobs, traditional mechanical engineering jobs. So, but within that job, even then, you will have this multidisciplinary advantage, I believe. All right, there's another question here. Hello, instead of choosing to specialize, it's possible to spend my modules to major. Yes. All right, with the new curriculum, and Tawakul mentioned this a little bit, there are so many opportunities, almost too many, so you really have to think a little bit. But you don't have to think on your own. You will have a mentor within engineering science. So you can talk to your mentor, you can talk to the professors, you can talk to me as a director, Jerome, deputy director. You can come to Liling and Joshua, talk about what you think, what you want to do, and get some feedback on it. But you can definitely do your first major with engineering science and then pick another major on top of that. And I think a major with physics is going to be a lot of double counting for modules, which will open up so that it will free up space for you to still have unrestricted electives, for example. And so the whole idea is for you to be able to, or one specialization, one minor, as I mentioned, or two minors. If you do that, I would still hope that you come and talk to me or to your mentor and get a little bit of feedback, because when I look at engineering science, I think that specialization is good to have. It's sort of in one specialization. I didn't talk about it much, but if you look at the module baskets of a specialization, you will find mechanical engineering modules, electrical engineering modules, physics modules, all across campus. And what we do is you not only take modules with ESP peers, but we also throw you into modules with electrical engineers. So suddenly you take a third-year module with electrical engineers, and they've only done electrical engineering. I mean, that's what they are doing. And we found that our ESP students do very well. And so you get a chance to work within ESP, but you also take modules outside where you get to network with other engineers or from science, humanities, and so forth to build your network a little bit. So I think with the build your curriculum, which is flexible now in the College of Design and Engineering, it's precisely that, for you to be able to be flexible, go with your passion. We heard philosophy being mentioned, for example,
yes,
where one could go in and do a minor in that. Major, tough one, but if it is doable and is offered, and I believe that more and more majors and minors are being opened up.
Yeah, like I got friends in my cohort, because I'm part of the new cohort. There's people doing events management, business, quantitative finance, physics. I think engineering science and physics, they go beautifully well together. Even other engineering, like there's one guy doing industrial systems engineering. Yeah, yes. So it's very, very flexible. I love it.
There's also a major and minor in design, for example. Design, the innovation design program that you could combine with ESP, for example. So there is a lot of options there. But I think with all these options, that you have a strong core, there's engineering science, there is fundamentals, there is very important. Something that, as Ibn mentioned, you can always fall back to. Say, in 20 years, you've been working, say, one job, and suddenly you find yourself entrenched. I'm almost 50. And learning new things becomes more difficult the older you get. I'm finding that out, even though I love learning. So if you learn the fundamentals way back when you were younger, it's much easier to go back to those and relearn, recapitulate what you learned. And I think that's going to be an advantage. Maybe we'll not see it so much yet, but with careers changing and you have to be flexible, we're going to see more and more of that. And in Singapore, that's lifelong learning, where expectation is that even after graduation, you will continue to take modules as you continue. Some could be sponsored by your company, for example. And I think in that context, ESP, engineering science, is well positioned, really well positioned.
Maybe I can add something which I got feedback from companies we collaborate with in engineering science program, lab practicals and internships. They mentioned artificial intelligence. We all know about it. But in order to get artificial intelligence to work properly, you need to understand the basic physics behind it. Otherwise, then it doesn't reach anywhere. So that's why this particular company really likes engineering science fundamentals, because you have the engineering mindset, but you have the physics principles, which allows you to properly think through things. He says otherwise he sometimes hires also engineers. He said they don't think properly through the thing, and then they, or at least the ones he sometimes hires, then it doesn't work. Artificial intelligence, you really need to think properly what you're doing. There's one of the feedbacks we got from industry.
Thank you, Jerome. Any other questions? You can hit us in the chat. You can send it to me directly if you wish. Any concerns? Anything that we have not touched upon? I think we've touched upon a plethora of aspects of engineering science with us and afterwards. I should have some background music to play.
Maybe I want to highlight one more thing which Ibnur mentioned, and which is really emphasized in our design modules, that you learn how to collaborate with people. I went to America, I went many times to America. Once I attended a big conference and they had a session on how to secure a job. So in that session, the person was saying, I mean, we understand that many of you, of course, you will have a good education in your university. But what is most important to get the job and a good security is that you're able to collaborate with other people. Because and employing your knowledge in a proper way, that is really important. And we emphasize, as mentioned, maybe some people went in or came a bit later, which we really emphasize in our lab design modules. You work every time in teams and the teams rotate, so sometimes it leads to conflicts, but we try to, of course we always try to then solve that, but it doesn't happen often. But still, it's a good learning experience. That's another thing I like to highlight. Yes.
There's a question here. I noticed that there is not CDP between ESP with Master Science and Science Management, while other branches have it. All right. I think what's happening right now with College of Design and Engineering being so new that we're still catching up with the minors and the majors and who can give what. So it's not set in stone yet. You can look at all the opportunities, but be flexible, be open, because more opportunities will pop up. So replying to the question here, it's not set in stone. And as we go along, more minors will be announced, more majors will be announced, and opportunities will come up. It's all being firmed up, yeah. A bit of a vague answer, I hear you there, again, to the question in the chat here. But that's what it is right now. Now, for those of you who have stayed with us, can I ask you, when you have the time, to go and, let me open up, to go in and give us a little bit of feedback. I think this should be the link to the feedback. You can log on and give a little bit of feedback, what you thought about Zoom crashed for me. Let me repeat it then verbally that please do provide feedback. It should be on the web page for NUS as well, once you've gone through the sessions there. Thank you so much for joining us today, ladies and gentlemen. It's been a pleasure having you here and interacting with you. And I hope to see you in engineering science going forward. Thank you so much. We will stay on if there are any questions until 12 o'clock. But let's end the official session now. Thank you so much again. Ibnur, thank you so much for joining us.
You're most welcome. Yeah, thanks so much for the invitation. Yeah.